Dear colleagues and friends, my name is Tarek Sobh. I am the Senior Vice President for Graduate Studies and Research and Dean of the School of Engineering at the University of Bridgeport in Connecticut, USA. I'm also a Distinguished Professor of Engineering and Computer Science. First of all, I'd like to thank the conference organizers for giving me this opportunity to be virtually present with you. And I'd like to also offer my sincere apologies for not being able to come in person, which I was very much looking forward to. But due to some logistical problems, this unfortunately could not be arranged. In this presentation, we are going to cover some recent advances in robotics, automation, and sensing. And in particular, this presentation will be in two parts. During the first part of the presentation, I will cover some recent advances and samples of exciting and interesting work within various fields in which robotics and automation have been deployed successfully. And then in the second part of the presentation, I will actually emphasize some of the work that has been done at the Robotics, Intelligent Sensing and Control RISC Lab at the University of Bridgeport. Just as a brief introduction to the city of Bridgeport and the University of Bridgeport in Bridgeport, Connecticut, University of Bridgeport has always been very well known for its professional and graduate programming, particularly within the STEM disciplines. STEM would be science, technology, engineering, and mathematics. As a matter of fact, the University of Bridgeport and the city of Bridgeport has been always touted years ago as the premier manufacturing city in the US. Actually, in the Second World War, the city of Bridgeport used to manufacture most of the US arms that have actually been shipped through the Bridgeport port to Europe for usage in the war endeavors. The very first milling machine ever invented actually was labeled for the manufacturing professionals within the audience as Bridgeport machines, due to the fact that the company actually existed within the city of Bridgeport. So the University of Bridgeport has had more than 87 years of history emphasizing professional and graduate education, in particular within the engineering, manufacturing, and automation disciplines. We are primarily situated in an area where there are lots of high-tech manufacturing companies, and in addition we actually do have a high-tech business incubator on campus. And we work with more than 700 companies within the area of manufacturing, engineering, software design, programming, computing, and the sciences. And one of the reasons for the existence of the Robotics, Intelligent Sensing and Control Lab are these environmental factors. And some of the work that I will cover later in the presentation will emphasize some of these endeavors. As a brief introduction to the rest of the presentation, robotics is a relatively new field of endeavor, and robotics is one of the areas that crosses many different disciplines, whether these are within the areas of electrical engineering, computer science, computer engineering, mechanical design and engineering, bioengineering, mathematics, and several others. The fact that the disciplines involved in the development of the theory and practice of robotics are very interdisciplinary are kind of interesting in academic settings. As an example, the Robotics, Intelligent Sensing and Control Laboratory at the University of Bridgeport employs tens of individuals, both undergraduate students, graduate students in the master's and PhD programs, faculty, and staff within the College of Engineering, Mechanical Engineering, Electrical Engineering, Computer Science, Computer Engineering, Bioengineering, and also several faculty from other colleges within the College of Arts and Sciences in the areas of mathematics, physics, and chemistry, and also other colleagues from disciplines like music and several others. In the next set of slides, I'm going to present some notable advances being developed in various industries and some interesting academic research laboratories and institutions other than the University of Bridgeport. Then I will be covering some exciting work that has been done at the Robotics Lab at the University of Bridgeport. We are going to cover several projects that are state-of-the-art within recent areas of endeavor within the robotics and automation area. First, we're going to show some examples within the area of swarm intelligence, and in particular some robot swarms that actually are not incredibly well developed as individual robots, but as a group they do exceptional tasks in a very collaborative manner involving the disciplines of intelligent agents, sensing, and many others. Then we are going to cover some very simple applications and recent advances within the area of telerobotic surgery and the applications of robotics to medicine. Following that, we are going to be discussing some robotic applications within the military domain, and then we are going to talk about some recent advances in a new and developing field, namely self-assembling, self-manufacturing, self-repairable, and self-maintaining robots and reproductive robotics. And then we're going to give an example of underwater robotics for the area of trying to gather intelligence from under the seas. In the following three examples, you will be looking at two types of robotic swarms. The first type of robotic swarms have been developed at Harvard University, and this represents on-the-ground robotic swarms. The second example will demonstrate a swarm of nano-quadrotors, and the third example will demonstrate swarm robots cooperating with a flying drone, meaning both on the ground and in the air robotic swarms. This work has been developed at various labs throughout the US.
Why send one robot to do a job when you could send 1,000? Harvard University scientists now have devised a swarm of 1,000 tiny robots that can work together without any guiding central intelligence. This is the largest team so far of self-organizing mobile robots. Working together, these robots can assemble themselves into stars, letters of the alphabet, and other complex designs. The researchers at Harvard's Weiss Institute for Biologically Inspired Engineering reported their work Thursday in Science. It is the latest innovation in the science of swarms. Swarm scientists are inspired by nature's team players, social insects like bees, ants, and termites, schools of fish, and flocks of birds. These creatures all collaborate in vast numbers to perform complicated tasks, even though no one of them is actually in charge. To give robots that kind of hive intelligence, the researchers resorted to fundamental guidelines encoded in software to guide the collective behavior. In the Harvard experiment, the researchers used inexpensive, off-the-shelf robots called kilobots. Each one is about the diameter of a penny. It has one infrared sensor and a simple vibration motor to move it along. Each of these robots knows three things: how to follow the edge of a group, how to track its distance from where it has started, and how to maintain a sense of its relative position. While still experimental, such big robot swarms one day may aid in oil spill cleanups, deep-sea ventures, military surveillance, and planetary exploration.
We developed a nano-quadrotor capable of agile flight. Multiple vehicles can fly as a formation. We developed a method to transition between formations in 3D. The team can also navigate in environments with obstacles.
recent trend in robotics is to get lots of robots working together. But parallel operation is not always enough. Some tasks are just too difficult for the robots to solve on their own. So-called self-assembling robots can combine forces by connecting to each other in a broad range of morphologies. But it's hard for the robots to know when to use different morphologies because of their limited local sensing range. The solution? Flying robots. Flying robots can analyse the environment to see what task needs to be solved, what morphology is most appropriate to solve that task, and which robots are best placed to form the morphology. However, it is non-trivial for the flying robot to communicate with specific robots on the ground. The problem is that the robots have very different views of the world, which makes it difficult for them to agree on a common frame of reference. We have developed a method that allows robots to select their communication partners without relying on any kind of global coordinate system. We refer to our method as spatially targeted communication. Let's say a flying robot wants to communicate with a specific robot on the ground. This one, for instance. To start the selection process, the flying robot illuminates its red LEDs. To join the selection process, the robots on the ground light up in blue. In a series of elimination steps, each ground-based robot independently displays a sequence of randomly selected colours. At each step, the flying robot matches the colour of the target robot. Whenever a robot on the ground sees that its own colour doesn't match the flying robot's colour, it eliminates itself. The process continues until only the targeted robot is left. An extended version of this method allows adjacent groups of robots to be selected and then given movement and morphology formation instructions. Here, the flying robot has already targeted the 4 robots closest to the hill and instructed them to form a line morphology. Spatially targeted communication expands the potential of self-assembling systems by allowing ground-based robots to benefit from cooperation with flying robots. Any robotic platform equipped with LEDs and a standard camera can participate in spatially targeted communication. Our current focus is on bringing our research out of the laboratory and into the real world.
In the following example will be a demonstration of telerobotic surgery using an existing industrial-strength robotic manipulator. Within the area of telerobotic surgery, many applications are possible, both for performing via a very skilled surgeon and thousands of miles between the operating table and the surgeon. Procedures within the area of orthopedic surgery, as an example, and there are also new emerging applications within the battlefield, where skilled doctors would be staying hundreds if not thousands of miles away from the battlefield, and actual robots with the appropriate sensors, manipulators, and effectors are performing via telerobotics using the skilled surgeons' techniques, surgeries on wounded soldiers, as an example.
The Da Vinci surgical system is the most advanced platform for minimally invasive surgery available in the world today. The integration of high-resolution 3D vision, wristed instruments, and intuitive motion control enable the Da Vinci surgeon to transcend the limitations of conventional surgical technologies, making new minimally invasive options possible for complex surgical procedures. 3 network components comprise the Da Vinci surgical system: an ergonomic surgeon's console, a patient-side cart with 4 interactive robotic arms, and a high-definition 3D vision system. Seated at the console, the Da Vinci surgeon views a remarkably clear 3D image of the surgical field. The system scales, filters, and translates the movements of the surgeon's hands on the master controllers to 4 interactive robotic arms on the patient cart. The DaVinci S HD system provides a magnified view that is both three-dimensional and high definition. The result is a phenomenal immersive experience of surgery. The precisely controlled micro-movements of the DaVinci instruments are enabled by the computer processors of the system. These dedicated processors perform millions of safety checks over the course of a procedure for enhanced surgical precision and control. DaVinci EndoWrist instruments are designed with a unique wristed architecture that provides 7 degrees of freedom for a range of motion greater than even the human wrist. This proprietary design enables surgical maneuvers impossible with conventional laparoscopic tools. As the surgeon operates at the console, the DaVinci system filters out hand tremor and translates his controlling motions to the articulating tips of the EndoWrist instruments. The DaVinci system also provides motion scaling that enables the surgeon to tailor the ratio of his hand movements to a corresponding micro movement at the instrument tip. The system requires that every surgical maneuver is under the direct control of the surgeon. Redundant safety checks prevent autonomous movement of the instruments or the robotic arms. The DaVinci S surgical system adds to the enabling characteristics of the original DaVinci to streamline surgery for the entire OR team. DaVinci S provides fast, foolproof setup, including a motorized patient cart for simplified docking, simple click-lock cannulas, rapid instrument exchange, and an intuitive touchscreen interface. Intraoperative communication between the entire OR team is enhanced with the audio-visual components of the system. The internal view of the operative field is visible on the vision cart or optional patient cart monitor. These monitors can also be toggled to display patient-critical information or a tiled display with multiple windows. Proctoring is enhanced with the telestration capability. Notations drawn on the patient cart monitor can be seen by the surgeon as an overlay on the surgical view at the console. The 2-channel endoscopic cameras of DaVinci S HD enable better 3D visualization of tissue planes and critical anatomy. The result is increased surgeon confidence and an environment that lends itself to greater surgical precision. LEDs that indicate status on each robotic arm, along with the user-friendly design of EndoWrist instruments, make intraoperative instrument exchange simple. Unlike conventional laparoscopic surgery, the robotic arms move around a fixed pivot point to reduce port site trauma for improved cosmesis and increased overall precision. The future of surgery includes enhanced visualization, superior instrument dexterity, and operative efficiency in a tightly integrated system. The DaVinci S surgical system moves surgery forward with a new level of technical capability that enables minimally invasive surgery in complex procedures as never before. DaVinci provides a streamlined surgical experience that benefits the hospital, the surgeon, the OR team, and, most importantly, the patient.
The next set of 2 videos represent recent advances within the military arena. In particular, you will see a little dog robot developed at the University of Southern California, and then followed by the Big Dog overview, which is a very significant military robot that has been developed by Boston Dynamics in Boston. And Boston Dynamics, as some of you probably know, have been recently bought, among many other robotics companies, by Google. These applications emphasize the military trend in many countries to develop both on the ground, flying, and in recent circumstances under the sea, robotic agents and devices that would completely replace the need for soldiers within any kind of battlefield, again, whether on the ground, on the seas, or in the air.
If you really jump, it's more difficult.
Sorry?
Really jump.
Oh yeah.
Like a stand up.
Yes.
But it jump like fall apart. Crash into it.
The following two videos represent recent advances within the area of self-assembling, self-manufacturing, self-repairable robotics. One of them is for a snake that is being self-assembled, and the other one is for a quadruped that is being self-assembled. The area of self-assembly and self-reproduction of robotics brings to mind the idea of being able to create sustainable environments. These sustainable environments could be in the future designed and manufactured via 3D printing techniques, as an example. And from a fantasy point of view, one can think that you will have the mother and father robot laying at night, and in the morning, once we come to the laboratory in which the father and mother robots are existent, you will see a whole self-sustainable environment with robots doing various tasks, repairing each other, and manufacturing new robots if the need arises. The next example will show an example of underwater robotics, and you will see the various degrees of freedom that this particular robot can demonstrate under the water with various types of movements. This is the beginning of the seed of trying to create self-maneuverable, autonomous, or tele-autonomous robots performing significant tasks under the sea. Now we move on to some of the projects being performed and done at the University of Bridgeport Robotics Intelligence Sensing and Control Laboratory. As a brief introduction to the RISC Lab, the RISC Lab has been founded approximately 19 years ago at the University of Bridgeport. The purpose of the Robotics Intelligence Sensing and Control Lab is not only to develop scholarly work and endeavors and prototypes using the work of the faculty and the staff and the undergraduate, graduate students at the University of Bridgeport, but also to work with industry hand in hand, in addition to the acquisition of several millions of research funding per year in order to develop state-of-the-art robotics sensing and control applications. The Robotics Intelligence Sensing and Control Laboratory at UB has graduated more than 500 students in the last 10 years or so, in addition to several hundreds significant scholarly publications and tens of millions of dollars of research funding. Most of the work that is being performed in the Robotics Intelligence Sensing and Control Lab focuses on the area of mobile robotic manipulators, the prototyping and design of robotics based on goal-oriented task descriptions, various sensing, reverse engineering, inspection, and swarm systems, and also some significant work within the area of software development for middleware applications and software for the control, design, and prototyping of robotic applications and automation applications. In the next set of slides, we are going to discuss some specific recent interesting projects within the robotics lab. And also, I would advise and recommend that you actually go and visit the link at the bottom of the slide that points to the Robotics Intelligence Sensing and Control Laboratory projects at the University of Bridgeport, where you will be able to find a wealth of information about the various projects that we are currently working on and recently have completed in addition to a complete set of the publications and the actual intellectual work resulting from the work on these particular projects. The first project we'll discuss is within the area of telerobotics, and these platforms are mobile manipulation platforms that we have designed and built over the years for various types of applications, including map building, navigation, manipulation, and also some recent work in self-maintaining and self-repairing and self-design for swarm applications. The second project will talk about an interesting project for a very practical application, namely tire changing for Formula One car racing. We also will discuss a project which has been recently displayed in museums in the US within the area of robotic musicians. In addition to some work that we have done for the area of reverse engineering of manipulators based on task descriptions, that is, the design and manufacture of manipulators, and modular robotics that can perform tasks that are specific with the ultimate possible efficiency, repeatability, precision, or based on the metric that is of interest. And then we will talk about recent work within the area of heterogeneous robotic swarm systems. In the first project that has been completed over several years in the Robotics Intelligent Sensing and Control Lab, you will see demonstrations of an experimental telerobotic platform that can be controlled over the web for various kinds of applications, including roaming hallways, determining maps for existing structures, and also for distance learning applications to teach, for example, a robotics class. So the first two videos you will see will be of the first experimental platform, namely RISC 1, and this demonstrates what we just mentioned. In the second set of two videos, you will see a highly modular and recently developed platform called RISC 2, which is a mobile robotic manipulator with redundant sensors that is very highly modular and scalable, with plug-and-play architecture from a software point of view that enables the design of various experiments using various modalities and sensors, even taking into consideration sensor failures and actuator failures, which will be the second set of two videos.
Go Great adaptive, modular and robust capabilities of the RISC-ware. 10 experiments were carried out on RISC-Bot 2. Different sensory devices, actuation platforms and software services can be selected to demonstrate desirable and optimal behavior. This experiment demonstrates manually driving RISC-Bot 2. Robot can be controlled by a human to move in any direction at initial speed factor of 2. User can also make adjustments to the speed factor. This experiment is similar to experiment number 1. In addition to manual robot control interface, laser rangefinder is selected as a sensory module. From the video, it can be observed that the addition of laser rangefinder does not impact the behavior of the robot. In this experiment, RISC-Bot 2 is under semi-autonomous control. Like in the previous experiments, a user can still control the robot, but the user is assisted by laser rangefinder. Laser rangefinder is capable of detecting obstacles at a height of 0.9 meters, and can use this information to navigate and avoid obstacles using potential field algorithm. Also, a wireless camera is active on the robot, allowing a remote operator to effectively control RISC-Bot in difficult-to-navigate terrain. RISC-Bot 2 is under complete autonomous control in this experiment. Laser rangefinder, which is capable of detecting obstacles at a height of 0.9 meters and at a distance of 6 meters, is used as the primary sensor for detecting obstacles. Robot is avoiding obstacles using potential field algorithm. Speed factor has been set to 2. This is to allow robot to be agile and allowing it to use all directions for obstacle avoidance. Like the previous experiment, RISC-Bot 2 is under autonomous control in this experiment. Speed factor has been increased to 3, allowing the robot to cover much greater distance in short periods. Also, 2 directions, namely front left and front right, have been disabled. This is to demonstrate the configurability of the framework.
The following project we discuss is a project about tire changing. In particular, some of our students were very interested in car racing. In particular, the idea of changing tire at pit stops in Formula One car racing, and it was noticed that the distribution of time and the race outcomes is very dependent on how fast and efficient this tire changing process takes place at the pit stops, and it's not uniquely a function of how skilled the driver is or how good the car is. Furthermore, it has been noticed that several accidents actually happened at pit stops due to the speed by which the workers need to perform the tire changing process, thus the need to automate the process. The solution that our engineers in the Robotics, Intelligent Sensing and Control Lab at the University of Bridgeport were able to come up with is a solution by which the pit stop is totally automated, with 4 upward hanging robotic manipulators that in tandem and synchronously do replace the actual tires in an automated fashion whenever the driver stops at the pit stop. The following video will illustrate the process and a simulation of how this would be done at the pit stops.
One problem associated with car racing is the time difference between teams during pit stops, which substantially affects the final results. In addition, a high percentage of the accidents is related to pit stop problems. Our idea is to build a fully robotized system that takes over the tire changing and refueling processes during races. There is practically no need for human intervention. The system demonstrates remarkable time accuracy, precision, low risk implications, and uniformity of performance across teams. Our proposed robotic system consists of 5 manipulators, all similar to the one presented in this simulation, 1 arm for each tire and a 5th one for refueling. To preserve the environment of the pit stop and to assure the comfort of the team, we implement suspended manipulators. The support of the 5 arms allows the sliding motion of each arm and also does not create any obstacles or driving difficulties for the pilot. The support has 2 double longitudinal branches on which the arms will be suspended, 2 arms on one pair of branches and 3 on the other one. Because the wheel of a Formula One car is attached with a single central screw to the body, there is design space for a flexible end effector with a low required torque and mass. By the time the car arrives, the robot sensor system registers it and notes the exact position and direction of the tires. Once the car reaches the full stop, the arms start the tire changing process. For lifting the car, a simple lifting system will be implemented and positioned on the stopping platform, which would suspend the car throughout the whole process. Each tire handling manipulator has to go through the following task sequence. Position the end effector as a function of the tire parameters received from the sensor system, rotate the end effector so that it can catch the tire, grab the tire, remove the screw, remove the tire from its axis and put it on the ground near the car in a convenient spot, change the position and grab the new tire located in the proximity with a new screw on it. Position again the end effector and fix the new tire on the axis, tighten the screw, move back in the standby position to enable the car's departure.
The next project was initiated by the music department at the University of Bridgeport, and the purpose of the project was to experiment with new types of tones and musical notes being produced not through humans and at the same time not digitally. In particular, there was intellectual interest in trying to see how classical devices could be either modified or used as is and played with several more degrees of freedom than a human would have. So for example, imagine the possibility of playing the piano using a robotic device, a humanoid that has 30 fingers as opposed to 10 fingers as an example. So the purpose of this project was to actually create a robotic musician band that performs on real instruments through the usage of mechanical devices such as servo motors and solenoids. The research involved included linking music, robotics, and computer science in a very interesting and comprehensive manner. Several of our engineers working with our musicians were actually able to perform this and create several interesting performances for live audiences using our robotic band. The following set of images represents some of the actual devices that we actually were able to complement with solenoids and actuators in order to enable our new devices to be recreated. This image represents the full robotic band, and actually we call it PAM, Partially Artificial Musicians Band. The band actually went on tour in the US and several performances were actually done. And now it resides in the museum, the Discovery Museum at the city of Bridgeport. The following set of slides describe an ongoing project at the Robotics Lab, namely the design and prototyping of robotic manipulators based on task descriptions. In particular, our engineers are very interested in designing manipulators based on user-defined tasks and operating constraints. Thus, whatever is to be created and prototyped in terms of a robotic manipulator would be quote-unquote perfect for the particular task that this particular manipulator is supposed to be doing, or set of tasks. The work involves lots of interesting new developments within the areas of workspace design and reconfiguration of the robotic based on the workspace descriptions, in addition to the various kinematics, inverse kinematics, dynamics, and trajectory generation required to perform a task. The project started by trying to optimize the parameters for manipulability. So the first phase of the project was designed to try to find the best manipulability envelopes for performing certain tasks, and based on these manipulability envelopes try to design and come up with the D-H parameter table in addition to potential dynamic parameters that would make that particular work and the particular manipulability requirements at particular points within the trajectory be performed optimally, and then come up with the appropriate design of manipulators with several degrees of freedom that can do the task in the most efficient and optimal manner. The following two examples show how a manipulator is to be designed for both a spherical goal task manipulability requirement and a ring goal task manipulability requirement. And the video shows, based on the requirements for the optimization of how to perform the task, what would be the correct manipulator to do the task in the most efficient manner. The following two videos shows a new developed approach at the Robotics Intelligent Sensing and Control Lab to find out all possible inverse kinematic solution using particle swarm-based inverse kinematics approaches. And then we show a simulated annealing structure for finding out the optimal solution among all of these possible inverse kinematic solutions to design a robot based on task descriptions. The following project is what we call the UB Swarm, the University of Bridgeport Heterogeneous Robotic Swarm System. This project, you see a set of very enriched sensory and activated set of robots that are very heterogeneous in nature, that work together very efficiently in a modular fashion, that are self-propelled based on task descriptions to perform tasks that a single robot or a homogeneous set of robots cannot perform. In the next two projects, you will see examples of work performed by these heterogeneous robotic swarm systems utilizing the many sensors that are on them, in addition to the manipulators and the many actuators that are existent. In this heterogeneous robotic swarms, we use a whole set of suites on each one of them, including stereo vision, that would be suites of sensors, including also infrared sensors, ultrasonic sensors, laser rangefinders, and others. This video shows one of the tasks being performed by the heterogeneous swarm robotic system. In particular, this task is about entering an enclosed environment and doing full mapping of the structure based on these robots collaboratively working together and designing and creating a map of the space that they are exploring. This video shows another application for the robotic heterogeneous swarm system, and in particular it simulates a human rescue operation in an unknown environment. And basically the idea is that these heterogeneous set of robotic swarms will be able to go into problematic areas in the case of disasters or fires or such events, and be able to recognize the existence of humans after exploring the space quickly, and then be able to perform an operation that would be similar to the one simulated here, which is in the case of pulling that particular human from the disastrous environment. In conclusion, I hope that you enjoyed the set of projects and ideas presented in this work, and I look very much forward to collaborating with many of the audience listening to this presentation. And we look also to having several of the interested students, both at the undergraduate and graduate level, join some of our research endeavors at the University of Bridgeport. Please feel free to visit our robotics lab website or directly contact me. All my contact information are on my website, which is displayed on this slide, and we would like to see further collaboration between us and the academics listening to this presentation, and furthermore to have several of the students interested in joining our research projects. Thank you very much for your kind invitation to present at your esteemed conference, and I look forward to interacting with you much more in the future. Thanks again. Best regards.